Today we are going to proceed from where we stopped in our previous class. In our previous class on latent heat, we talked about what latent heat is. Then I gave you some examples on latent heat, how to calculate what the latent heat, that's the heat absorbed or the heat was given off when we convert ice at a negative temperature towards steam. I gave you a simple diagram we used to do some of those calculations. Today, I'm going to do some more calculations under latent heat. Some we are going to make use of that same diagram. Then some we may not make use of that diagram because it may not be necessary for some of the questions we are going to solve today. Now, when necessary, just like we did in our previous class, we take the specific latent heat of ice at 335 joules per gram, specific latent heat of water as 2250 joules per gram, specific heat capacity of water as 4.19 joules per gram per Kelvin, then specific heat capacity of ice as 2.14 joules per gram per watt Kelvin. If you are given the mass in kilogram, all I need to do is to convert, either I convert the mass from kilogram to gram, then work with these parameters given here, or we just multiply each of these things by 1000 to convert to joules per kilogram, or to convert to joules per kilogram per watt Kelvin. In every exam you are going to write, when you have questions to solve on latent heat or specific heat capacity, you are going to be given all of these parameters because they are constants. All right, let's proceed. Let's look at the first example. Example 1. Calculates the heat required to convert ice, convert 30 grams of ice at minus 5 degrees C to water at 40 degrees C. Now, in our previous class, we did something similar to this one, so that's why I want to start with this one today. Today, I'm going to look at some short questions under latent heat. Then in the part 3 of this series, we are going to look at some lengthy questions, just because of those that may be doing some theory exams that contains objective and theory. So I'm going to do that type of question in the part 3 of this series. So ensure you watch out for that particular series, which should be uploaded soon. Let's look at this question first. Now it says calculate the heat required to convert 30 grams of ice. That's the mass of the ice. Is 30 gram at minus 5 degrees C. The initial temperature is minus 5 degrees C to water at 40 degrees C. To water at 40 degrees C. Now 40 degrees C represents the final temperature. So what I will do from what we did in our previous class, I'll draw this diagram. I have to do it ice at minus theta to steam at 100 degrees C temperature with what time? Okay, changing temperature with what time? Now the ice lies at minus 5. So here I'm going to put minus 5 so water at 40. Remember, here is water at 100. So we can pick a point here. Let's call this point water at 40 degrees C. So based on what we have here, the total heat required, first we're going to calculate from this point to this point first. And then we'll move from here to this point. And then after we'll move from here to this point. So we're going to have 3 different calculations, okay, for us to obtain the total heat required. So first thing I will do is the heat required to convert ice at -5 degrees C to ice at what, 0. You convert ice first at -5 degrees C to ice at what, 0. So we get what, H. Heat required to convert ice at -5 to ice at what, 0. Heat required to convert ice at -5 degrees C to 0 degree what, C. That's ice at what, 0, not water now. So the first thing I'll do, I'll have NC change in theta because there's an increase in what temperature. The mass of ice is what, 30 grams. So I have 30 times the specific heat capacity of ice, that is 2.114, times change in temperature. The change in temperature will be 0 minus -5, and that is 0 plus 5, and that is 5 degrees C. So we'll have that. We multiply that. If you multiply that, let's see what we get. 30 times 2.14 times 5. So that will give us 321. That was 321. Okay. So the next thing I'll calculate is heat required to convert ice at 0 to water at what, 0. Ice at 0 to water at what, 0. So that will be M1 L. M1 L, but there's no increase in water temperature. That's the mass of ice times the specific latent heat of what, fusion. Specific latent heat of what, fusion of what, water. But at this point, when the ice is at 0 from here to here, we have what, water. So we have the mass, which is 330, times specific latent heat of what, fusion of what, water, which is what, specific latent heat of fusion of ice. That is what, 3315, 335. Specific latent heat of fusion of ice. So we get 30 times 3315. That will be 10,000 feet. So the next thing I'll do is to calculate the heat required to convert the ice now plus water now. But at this point, it's not water. At this point, we have ice at what, 0. Okay? So the ice will melt to what, water. Hence, we're using what, the specific what, latent heat of what, fusion of what, ice. Okay? Now, at this point, where we have 100, this is what makes of the specific latent heat of what, vaporization. So that's where water will vaporize. So now that we have calculated the first one and the second one, so from here to here, the heat required to convert the heat required to convert the ice, which is now water at what, 0, water at 0 to water at what, 40. That will be H equal to MC change in what, theta. That's the heat required to convert water at what, 0 now, for the ice has melted, water at 0 to water at 40. So that will give us MC change in theta. So the mass is 30 times. This point now, talk about the specific heat capacity of water. Specific heat capacity of water, that's 4.19. Then times change in temperature. Change in temperature is going to be 40 minus what, 0. 40 minus what, 0. And that will give us 40. So now let's do that multiplication. We have 30 times 4.19 times 40. 30 times 4.19 times 40. Well, it was 5028. 5028. So the next thing I'll do is now to calculate what the total work heat was required. So total heat required is obtained now by addition. The total heat required, you can now obtain that by addition now. So we have 321. Now 321 plus 10050 plus 5028. We add up that now. 321 plus 10050 plus 5028. That was 15,399 joules of what heat. So that's the heat required to convert the 30 gram of ice at -5 degrees C to water at 40 degrees C. So from the diagram, it's easy for us to know the number of calculations we are going to do and the exact formula to apply. Here we know there's an increase in temperature. Here there's no increase in what temperature, SML. Then here we have an increase in what temperature. At this point, we're talking about ice. So the ice will increase to have what the specific heat capacity of what ice. Makes the specific capacity of ice as 3315. Sorry, 2.14. Then at this point, we have what the latent what heat. Okay, the mass times what the latent heat of what fusion of ice. Then you'll make use of what the mass times what the specific heat capacity of what water. Or add up to get what 15399 joules. Okay, let's take a look at another example, slightly different from this now. Like I said, I'm going to do some examples different from what we did in our previous class. Let's see example 2. Example 2. Says calculate the heat energy required calculate the heat energy required to vaporize 50 grams to vaporize 50 grams of water initially at 80 degrees C. Now, for this particular question, it says to calculate the heat energy required to vaporize 50 grams of water initially at 80 degrees C. So what I will do, the same diagram now. But this time, we are talking about 50 grams of water initially at 80. Remember, this top point is 100. So let's mark the point here. Let's call this point 80. To vaporize, so that means I'm moving to this particular point. So I move from here to here, then from here to this point. So I have 2 calculations. So what I'll do is the heat required now. So I'll just keep the writing parts. I'll calculate what the heat required to convert water at 180 to water at 100. There's an increase in temperature. So I'll have MC change in theta, plus the heat required to vaporize was water at 100. Now to convert water at 100 to steam, that was M of L, which is what the mass times what latent heat of what vaporization of what water. So now the mass given is 50. Specific heat capacity of water, that's 4.19. In change in temperature, that will be 100 minus 80. 100 minus 80, that will be 20. That will be 20. And the mass, 50. Specific latent heat of vaporization of water is 225.0. Now, some said they might give this as specific latent heat of what steam. The same as specific latent heat of vaporization of water. Okay, let's do that multiplication now. We have 50 times 4.19 times 20, plus 4.190 plus. We have 50 times 2250. Now the 112, 500. Well, we get 116, 690 joules of what heat. That is the heat required to vaporize 50 grams of water initially at what 80 degree watt C. So you can see how easy it is when you are making use of this diagram, especially when you are talking about what ice, when you are talking about what water. Okay, it's just easy making use of this diagram. It helps you to know the number of times you are going to do the calculation to obtain the required answer. It is not something really difficult. Just try to understand the question itself, then bring out the parameters in the question. Once you can do that, you can solve for the question. Let's take a look at another example. Example 3. Is a 90 watts immersion heater. A 90 watts immersion heater. The 90 watts immersion heater is to supply energy. Supply energy for 5 minutes. 5 minutes. The energy supply is used the energy supplies is used to completely melt to completely melt 180 grams of a solid. 180 grams of a solid at its melting point. At its melting point. At its melting point. First of all, neglecting energy losses. neglecting energy losses. Neglecting energy losses to the surroundings, calculate the specific latent heat of fusion of the solid. Neglecting energy losses to surroundings. The surroundings. Calculates the specific latent heat of fusion of the solid. Specific latent heat of fusion of the solid. Okay, let's take a look at that question. It says a 90 watts immersion heater used to supply energy for 5 minutes. It's used to supply energy for 5 minutes. 12 hour 90 times 5 minutes to convert to seconds. Now 300 seconds. So the energy supply is used to completely melt 180 grams of water. First of all, what's the energy supply here? Energy supply, the heat energy supply, is power times your time. And that would be 90 times 300. That's the heat energy was supplied. So that's 27,000 joules of energy. Now it says the energy supplied is used to completely melt 180 grams of a solid. So the mass of solid 180 grams of a solid at its melting what point? At its melting what point? That means there is no change in what temperature, because the solid is already at the melting what point. Since the solid is already at the melting point, there's no increase in what temperature. So I'm going to make use of what M what L. So calculate the specific latent heat of fusion of what the solid. We're looking for what L. Now H equals PT, and that will be what M what L. So we have 27000. The mass of the solid is given as 180. A specific latent heat of fusion of the solid. So that's the formula we apply. Apply that formula, we can get the value. That's 27,000 divided by 180. Value was 150. Value 150 plus L is 150 joules per gram. That is the specific latent heat of fusion of the solid. Remember I told you anytime you have an electrical appliance, heat is equal to what? Power times for time. Okay? Power times for time. And you also know that P is equal to IV. So from there, we can obtain other formulas to get that. You see a question like this as we proceed. I'm going to show you that. You look at our series on quantity of what heats. Yeah, I think part 1 of that series, we talked about how to calculate heat and quantity of what heat. I made reference to some of the formulas I'm talking about now. So if you have not watched that series, try and watch that series before you continue with what we're doing here. You get a better understanding of what we're doing now. Okay, that's example 3. Let's take a look at another example. Please ensure you subscribe to our YouTube channel. If you feel you are gaining something from this particular video. Okay, let's proceed. Let's look at example 4. Example 4. Example 4. The 10-ohm coil takes 21 seconds. Takes 21 seconds to melt 10 grams of ice. To melt 10 grams of ice at 0 degrees. So assuming no heat losses, assuming no heat losses, determine the current in the coil. Determine the current in the coil. Okay. Now let's take a look at a question. Let's see how we can solve that one. Let's see a very simple question. Let's see. It says the 10-ohm coil that speaks of what? Resistance. Resistance takes 21 seconds. That speaks of time. To melt 10 grams of ice mass. 10 grams of ice at 0 degree was initial temperature of what ice. 0 degree was C. As we know heat loss to the surrounding, determine the current in the coil to melt 10 grams of ice. Let's make a first of this diagram. Ice at 0 is almost at this point here. That's ice at 0. So we're going to melt the 10 grams of ice. I'm moving from here to this point. From here to this point. So I'm going to do one watt calculation for that. Now, as we know heat losses determine the current in the coil. So I'm looking for what I. We're looking for what I. So remember, H is power times time. Since we have resistance, we're looking for current. P is equal to what IV, and V is equal to what IR. That means P will be I squared what R. I squared what R. So that H will now be I squared R what C. So I squared R C, that's the heat supply now, will be equal to what? M what L. M what L. So the currents, we're looking for the currents. I know it was the surrounding determine what's the current. We're looking for currents. Since we have to calculate currents, I square R. So I get I squared times R is 10 times 21 equals the mass of I is 10, the specific latent heat of fusion of ice, that's 3315. 335. So this one gives us 210 I squared equals 33510. What I'll do first to divide both sides by. I'll divide both sides by 210. So I'll get I squared as 3350 all over 210. All over 210. That was 15.95, approximately 16. So that I will now be square root of 15.95. Now it was about 4 ampere, approximately 4 ampere. That'll be approximately 4 ampere. 3.99, and approximate that to 4 amperes. That is the current was required. That is the current required. So like I said, it's not something difficult, okay? Part of what I did here now, I also did that in that topic where I was talking about what the quantity of what heat. So ensure you look at that topic, possibly after this one. Let's see another example, example 5. Example 5. Is an electric kettle. An electric kettle rated at 1,500 watts. Boys away 0.3 kg of water, 0.3 kg of a liquid, rather, of a liquid at its boiling point. At its boiling points. At its boiling points. In 300 seconds. In 300 seconds. Calculate the specific latent heat of vaporization. Specific latent heat of vaporization. Of vaporization of the liquids. Okay. That's the question. Let's see how we can do that calculation. Say an electric kettle rated 1,500 watts. That speaks of power. 1,500 watts. Boils away 0.3 kg of a liquid. That's mass of 0.3 watt kg of a liquid at its boiling point. So that means there is no change in temperature. in 300 watt seconds. That's piece of time. 300 seconds. Calculate the specific latent heat of vaporization of water. The liquid is at what? The boiling point. So heat H equals power times time, and that will be equal to what? M what? L. Pi is 1500. The time is 300. You will have 0.3 watt L. So I'll give us 45 equals 0.13 watt L. So we'll divide both sides. Divide both sides by 0.13. Divide both sides by 0.3. You get what the latent what heat. So we get 15. Okay. So I have 1.5 times 10 to the power 1, 2, 3, 4, 5, 6 joules per kilogram. Okay, that's the value of what the latent what heat. That's the value of the latent heat of what vaporization of the liquid. Just remember that what heat equals what power times time, and that's equal to what NL or NC change in theta. You have more than one calculation, because sometimes you can have heat equals NC change in theta plus M with L. It all depends on the particular question that you are given.